The idea of this exercise is to calculate the forward kinematics of a robot with only two links, and that moves in 2D. So, as I explained on one of the lectures, this can be very easily solved with trigonometry. And we know that, we can calculate the position x of the n effector with, this formula here, the position y of the n effector with this formula here, and then the final angle of the n effector is going to be alpha plus beta. So the idea is to write a function that takes as an arguments alpha and beta, and also we will need to know as an arguments like the length of the links. So we have two links, so we need to know their sizes. And then it's going to return x, y, and theta. So we provide the angles of the joints, and it's going to give back to us like the position and the angle of the n effector. So as you can see here, we will need to use cosinus and sinus operations, which we can get access to them using the math module, as I saw in the first lab lecture. And then something that is important is that, we usually think on degrees, like 90 degrees or 120 degrees or something like that. But as you know, there is also like the angles can also be represented in radians. And actually Python works by default in radians. So as you will see on the code, I will need to convert between one or the other. Anyway, so let's start with the code. Let's see, I'm going to zoom in a bit. So the first thing I'm doing is that I'm importing math. So now I have access to the different math operations, such as like sin of 3, for example, and it returns this value. Anyway, so let's make a function to calculate the forward kinematics. So the first thing that we need to do is that we need to write the word def, and then, well, you can see now in gray because I was practicing it before. Like, IPython remembers what I did before, but anyway, I'm going to imagine that I never did this before. So I start with the word def to tell to Python I'm doing a function, and then I'm going to name these functions forward kinematics 2D, for example, for a planar robot, and it is going to have 3 arguments or parameters, which is what the user is given. The idea is that I give an alpha and beta, the angles of the joints, and I want to calculate the position and the angle of the n effector. So I need to provide, the angle alpha, the angle beta, and then I need also to provide the length of the links. In this case, links is going to be a list with 2 parameters. Something that is important is that I was saying it's important that the user that is going to use this, in 6 months, needs to know if we are expecting as inputs radians or degrees, because depending on that, the results are going to be very different. So we actually don't have a way to enforce it. The only thing we can do is to, write a comment to tell to the user that, that we are expecting degrees. So for example, here we can say something, alpha and beta must be in degrees, not radians. And we can also write a second comment, for example, to say like links must be a list with 2 elements, length of links. So for example, the person in the future is going to work with this, is going to read these comments. I will say, okay, so alpha and beta need to be on degrees, and then links needs to be a list. Fine. So the next thing that we need to do is that we actually need to calculate the values of these angles in radians, because that's what Python is going to do. So we can do something like alpha in radians, which is going to be equal to math radians alpha. So basically math radians is a function in Python that is going to get an angle in degrees, and it's going to return its value in radians. And we can do the same with beta radians. So math.radians beta. So now we have converted both alpha and beta into radians. So the first thing that we can do is that we can calculate the value of theta, and as you can see on the slide, the value of theta, so the final angle of the n effector is just alpha and beta. So this is actually, super simple to calculate. So we can say something, like alpha plus beta. And then we can all finally get it on degrees by say that, so here we do alpha plus beta in radians, so we get theta based on the formula from the slide. And then finally we convert this angle from radians to degrees. Obviously what I've just done now doesn't make like it works, but the thing is that we already had alpha and beta here on degrees, so we could just add them together. So doing this calculation is actually, not needed, but I just showing how to make it. So the next thing that we are going to do is that we are going to calculate the position x of the n effector. And basically what you need to do is to follow this formula here. So I'm going to put this besides. So basically we need to multiply the position 0 of the link, so the first link, multiply by the cosinus of the alpha angle, and then the length of the second link, and then multiply by math.cos. You cannot see it here, but basically it says like the position x e of the n effector here is equal to the first link multiplied by the cosinus of the angle alpha plus the length of the second link. Actually, I did a mistake here. It's not 2, it's 1. Remember that the list starts with 0. Multiplied by the cosinus of alpha and beta. So this is going to give us like the position of the n effector on the x-axis. So now actually the calculation of y of the n effector is exactly the same, but using sinus instead of cosinus. So we can just copy the line from above. So I'm just copying that line. And now finally we have x, we have y, we have theta, so we can just return it. So, oops, x, y, and then remember that theta is alpha plus beta, so I can just do something like that. So now we have our function that calculates the forward kinematics of a planar robot. So let's say, for example, that alpha is 40 degrees and beta is 40 degrees and the links are length 2 and 3. Oh, so I did a mistake, so this is actually good. You could see that here I did a typo, like maths. I don't know why I put maths instead of math. So I just fix it. And now I execute forward kinematics again. And it says that if the first joint is at 40 degrees and the second joint is at 30 degrees and the links are 2 and 3, the position of the n effector is going to be 2, 5, 5, 4, 1, 0, and 70. And let's say, for example, both angles are 0 degrees. So the position of the n effector as expected is 5 because both of them are like over the horizontal, 0 on y, and the angle is 0. Anyway, so this is the solution of the problem. It was just basically copying in Python like the formula from the slide.